Yeah, thank you, Will. Thank you, everyone, for having me. Yeah, I lead a team in AWS. It's called Amazon AI. Our charter is to build models, to build services, to enable machine learning, to enable engineers and our customers to use machine learning in different fields. My personal background is, as Will said, in language technology, and this is what I'm going to be focusing on in this presentation. So, computers and humans communicate with each other since the computer started, obviously, because we need to tell the computer what to do and how to calculate. So I'm going to go through, I'm going to go down memory lane with you, and we'll talk about the different generations of computing. So this is the initial way of how we communicated with computers. There's punching cards, and there's mainframes, and it's complicated. We need to basically understand how the machine works so that we can communicate efficiently with the machine. The output was a terminal or a printer initially, and it was all quite awkward. Second generation is a personal computer. So it's much more closer to how we think, how we work. We have keyboards, we have joysticks, we have mice later on, and the output is a monitor. It's much more interactive. We can communicate with the computer. Still, we need to understand how it generally works, but we don't need to understand, for example, assembly. I don't need to understand. I don't need to be an engineer to interact with the computer anymore. Initially, it was text only. Later, we had graphical user interfaces. Things gotten much closer to how we think. I mean, the way on the time until I am efficiently working with the computer is much faster. The third generation is mobile computing. So we are using mobile devices every day. It's getting more easier. It's closer to us. Swiping, maybe speaking into the system, and so forth are things which we can use the computing with. So we have virtual keyboards, we do swipes and taps, and the output is right there in the screen in our pockets. The fourth generation, we believe, is the ubiquitous computing. So with computing being in the cloud or on the edge, we are communicating with devices still with a screen in our pockets, but they might not even be with us anymore. If I'm at home, I don't carry my cell phone around. There's Alexa in the corner listening to the wake word and then starting the computing in the cloud, and then I can communicate, I can ask, I can start processes very naturally, the same way like I would do if I would be talking to a human. So the machine adapted to us, it's closer to how we are working. So to get there, we went actually through a lot of steps also on the human language technology side. So to talk about the dialogue system, how a system similar to Alexa works, or what we have developed in Lex, which is a service where you can build user interfaces similar to Alexa in other formats. Typically, a system works like this. We have a speech recognition engine, we have a dialogue system, and we have a speech synthesis, which does the communication, makes the communication human-like with language. Theoretically, I mean, the reason why we had to split it up over the last years is we did not have at that point initially when we started working on dialogue, we did not have enough data to train systems in a fashion where we would directly learn one system to do human utterance and machine utterance back. So we needed to break up the problem into different sub-problems. I'm going to start talking about speech recognition. Again, going through the down memory lane here, Speech recognition is not a new task. I mean, in the 50s, DARPA funded speech recognition quite a bit. The task of TI digits, which you will still read in some of the publications, was then established. We had to recognize, not we, people before me, had to recognize 11 words and basically the digits. Things were template driven. The big players there were Bell Labs and IBM, and they built things which looked like this, where basically the system was doing the speech recognition. You had a microphone and communicating through that microphone into the system. In the 70s and 80s, DARPA started slowing down funding in the mid-70s and ramped it up again in the 80s. That time is where the HMMs gotten into the world of speech recognition. And beam search and lattices and language models, and the big players there were Carnegie Mellon and IBM and BBN and SRI, etc. At that time already, some people experimented with neural networks. Alex Weibel, for example, tried to do neural networks, similar concepts like what we would call today CNNs. He implemented and did some speech recognition, but still the systems which were basically state of the art were mostly HMM based. Here you see basically systems which were running that way. So the systems, the tasks gotten more complex. We are recognizing thousands of words now, 1,000 words with a few speakers. It was not speaker dependent anymore, but the error rates were still, relatively high. So you see, for example, HWIM was in the 50s, and even though the task is what we would call today quite simple. The approaches gotten more complicated, but the computing was more powerful, so we started working with alternative graphs, word graphs, and so forth. So that, and also multiple levels of representation of what speech is. This represents, for example, HMMs on character levels, and that's what was basically state of the art in the 90s. We were working on HMMs in the phoneme level. Companies started to get established which were doing speech recognition commercially. Dragon and IBM and Apple and other companies which are now, for example, in part of Nuance. So in the 90s we started seeing commercial applications like dictation systems and also the initial systems where you can basically communicate through voice with the computer. So for example, Apple came with the Plain Talk microphone and Plain Talk, where you can do system transactions using voice instead of using the mouse, which was revolutionary at that point from the user perspective, but it did not get the adoption which we were hoping for. In the 2000s, Apple saw it was not very, it didn't go the way it wanted, but in the 2000s we started also collecting data. New players came to the market, like Google came into the market, and basically we started due to the data which existed, we started seeing that speech recognition improved quite a bit. In 2010, then the deep learning wave came with speech recognition showing a drastic improvement, up to 30% reduction in word error rate, that we started seeing the results which we use today. And we have data now which is much more. We have companies like Apple, Google, Microsoft, and IBM ramping up quite a bit. New players coming to the market like Amazon and Baidu. And new applications came to the market which we were not even dreaming of when we started doing research in speech recognition, which is super cool. Okay. So as you see here in this graph, I borrowed that from the Economist, which again borrowed that from different papers. You see that the error rate, decreased over time quite a bit. Things like broadcast speech went down from the 50s word error rate down to 10s, which is very good. Problems like switchboard, basically conversation through the phone, where basically in the early 90s, almost 100%. Today we're talking about in the 5% range, which is very, very cool. Now, if you see this, you will think that speech recognition is solved, which it is not. We have a lot of use cases in research where we're not in the 5%, we're still in the 30s and so forth, where it's very noisy, where languages come and mix with each other and so forth. And so the research is going to continue for the next, 15, 20 years at least. So I'm happy that our job is safe. So text-to-speech is the other component which makes dialogue work quite well now. So if you look here, text-to-speech is also a very old research area, but it improved quite a bit. First it was, we had a lot of rule-based approaches doing text-to-speech. Today and I can give you a few examples here. Deck Talk is something which probably you guys might have heard before. I'm gonna play in a moment how that sounds. So we have a lot of things which needed to be developed without data in the beginning, and then later on we went and used data as a source and learned from it. And I'll give you an example of text-to-speech, how it sounded in the 70s, like this.
Hello, Wikipedia. This is Deck Talk speaking. Right now, you are hearing my perfect call voice. However, I also have other presets.
This, for instance, is loud here, so a voice city.
As you can see, this came from Wikipedia, and it was good, and it worked quite well until the 90s and even 2000s. But so we started building better systems which are using concatenative speech, concatenative synthesis, HMM-based, and so forth. Now we have deep learning, which makes it even better and sounding much more natural, like this.
Hello. Do you speak a foreign language? What language is never enough?
So this is our poly voice. As you hear, the naturalness is gotten much better. And the advantage is that we have much more data. The advantage is that with the computing power which we have, we can allow for more context, more. So it's not very local. The decisions on how basically text is synthesized or speech is synthesized is not only dependent on local information, but I can look into the sentence, how the sentence melody should be looking like, and make a sentence sound much more natural. Beginning of the sentence should sound different than end of the sentence, etc. And now we're working also on adaptive text-to-speech technology. So you don't need as much training data. You can basically build on something which you have as a baseline and adapt towards a specific voice, which is also a cool area of research. So now we talked about speech recognition, and we talked about text-to-speech, and now we're going to talk about the dialogue system itself. So dialogue systems came also in multiple generations. The first generation is rule-based mostly. People had to basically write down the behavior of how dialogue should look like. If I have certain words spoken, how do I react to it? So some of you might remember ELIZA, for example. I consider that a rule-based approach. Later in the 90s, companies came together, teams came together and decided maybe we should formalize it specifically for that, for dialogue systems, and they came up with the voice XML formalism, which helps building systems, and it's until today very commonly used in different areas. But then there is also other ways of building dialogues by basically developing automatic parsers and classifiers on what is an intent and what is a slot, so that I can basically connect certain business logic to certain intents and fill slots and make these transactions possible. So the second generation is using more semantics. We can move away from being very concretely describing what words I need to see into more what is it what semantically I want to see? What is the concept I want to see? So by using concepts like embeddings or attention models, we can basically build things which are, you basically as a developer don't need to find all possible ways of saying how to order pizza, for example. Just a few utterances will give you enough will give the system enough information on what is it what I need to basically be paying attention to and what to do from there. Slots exactly the same, so we don't need to identify all the values which I want to see. I basically just need to say I want a certain food item or I want a certain flower item, and then basically the system will figure out what you need what it needs to do. So this is basically what the system looks like today. I mean, usually we have a natural language understanding component which basically identifies the intent and the slots, and then we have something which we call dialogue state tracker, which identifies the context of a conversation, where I am, what kind of question did the system ask, what the human is answering, so that we can combine information intelligently together and then basically trigger certain policies. What do I do after I see things? Do I need to ask a question back? Do I trigger something in the business logic and go from there? Now, with all these cool new things we have, multitask learning, zero-shot learning, reinforcement learning, imitation learning, enhanced embeddings and attention models, we can use more context than what we had before, which is very good. And that comes to the next point here. Multimodality and multilinguality in that context is very important. If you are multilingual, you know that in a natural environment between you and the partner you're talking to, the other human, oftentimes you mix languages with each other. So something like that should be possible with the dialogue as well. The other thing is also when we converse, we use more signals than just the language, and that's something which we should include in the dialogue as well. Also, with these techniques, now we can basically connect the understanding and state tracking together, and the policy engine, the generation, to be one model. We can think about putting them together and see that there is an end-to-end system built which can learn from conversations, because we have data. I mean, for example, customer service at Amazon, you have a lot of conversations, millions of conversations in a month. You theoretically can take that data and learn from it. How does a customer service agent interact with the customer to achieve a certain goal the best way possible? So we go from this kind of picture to, I mean, you can basically put the blue box, the dialogue system, all in one box. But what if you can even go further and say, okay, I mean, if we have the data, which is all speech, we could theoretically think about taking speech recognition and dialogue engine and speech synthesis and put them all in one box together. Now, this is very researchy. I mean, this doesn't work very easily, but that's something I think which we're gonna see in the future if we have enough data for this. So we have an end-to-end dialogue system for speech input, but what if we can go even one step further and say human input and machine output, and independent of modality, text input or speech input? That's something which is also part of the research which people are working on. So some applications. You see here a lady putting products in, picking products, as we call it, like for an order which she is fulfilling. She is conversing with the computer, informing the computer about the status of the items she is picking, or whether a box is getting empty or not. She's using a multimodal approach here, so it's not only the spoken word, she is using also a scanner in her hand, for example. This is also part of the dialogue. So that's one application. Then, of course, as we heard earlier, car. I mean, you have to keep your hands on the wheel. So it's a very important thing that dialogue systems should be able to remove the need for focus from you. So they need to be as natural as possible with you. But also areas in health, for example, you have use cases there. Call centers, super important, very important component. I mean, that's probably still the bulk of the business of dialogue. Other areas are like in the legal area. Meetings, I mean, some people are building agents so that meetings can be accompanied by an agent and do things for the meeting people who in the meeting. And then, of course, Alexa. But also Alexa, we have the Echo Show, which is already multimodal. It has a camera built in, and it has a screen. So conversation is not only spoken, but you can also hold an item in front of it and ask questions about that item, for example, or shop that item, etc. And there's use cases which are gonna come, and some startups are working on where, I mean, robotics and conversation are connected. And I think that's going to be a very important way of conversation. or communication with those items, with those robots. So yeah, we as AWS, Amazon AI, we offer basically the building blocks for different things. I mean, to build chatbots, to build agents, we have Lex, but we have many other components which can combine with that, and that's yeah. Thank you very much for your attention.